type of sugar am I dealing with here?
Sucrose.
Sucrose, yes, table sugar. Which is made from what two types of sugars? Fructose and glucose. Excellent. Write down, whoever has the packet, your observations about what the sugar, sucrose, looks like. It's a white crystalline solid. Write that down.
What?
On the question with the notes. Yes, thank you.
There's an observation spot.
Next. Clear, colorless liquid. Clear, colorless liquid. Nope. It is 18 molar. 18 molar. It's really strong. It's nasty stuff. That's why I've got the special chemical gloves on and why we're in the fume hood. One of the reasons why we're in the fume hood. What is the unit for molar concentration? Moles over liters. Absolutely good. So it is 18 moles over liters. So there are 18 moles for every 1 liter of liquid that we have in here of the sulfate ion and H3O hydronium ions. I am going to pour the liquid into the sugar. It's not going to react right away. What I am going to do is stir it a little bit. If I wanted the reaction to increase, what could I do to increase the rate of the reaction? Stirring it would be one thing. What else? Heating it up, yeah. Pressure, if I was dealing with what type of substance? Gases, absolutely, which I'm not here, so that wouldn't work for me. Increasing surface area or increasing concentration, which this is the highest concentration that I can buy, so that would not work. And increasing the surface area is kind of what I'm doing with stirring. So let's see what we get. Write down your observations carefully. Yep, it becomes yellow.
It's lemonade.
It is not lemonade. Nice try.
Now it's a slushy.
It is not a slushy. I'm going to stop stirring it right now, and I'm going to tell you why later. Yep, it's turning kind of brown. Not iced tea. Definitely not root beer.
Looks like it has an ice cube in it.
If that was your root beer, that would be gross.
Now it's black.
Now it is black. Now make those big noise. There's chunks of solid in it. I like that a lot. It's like, have you ever seen what's
Oh wait, we actually like make it rain. We make it fly. If you make it acid rain.
I know it started to react, but it hasn't quite hit that activation energy fully yet. So we need to be patient.
I would presume. What kind of reaction does that?
Oh, it's smoking. Look at it. What's happening to the volume?
It's alive.
Yes.
It's alive. It's alive.
It wasn't gross. It's not gross. It's so cool. It's so cool. Most of it is just regular carbon.
It's a pencil.
Kind of. Oh, look at it bouncing there. Bouncing a little bit.
That's really marble.
It is not
Flubber.
It's definitely not flubber. It is really hot in there right now. You are absolutely correct. It's very exothermic. We're not going to have anybody touch the side of the container because it'll burn you. What we are going to do is go back to our desks because we have to discuss this a little bit. So back to those desks facing forward, please. Looking at some of the questions we were dealing with, I put the H2SO4 in parentheses here because really there is a reaction that's occurring there. It's not just a catalyst, which if we put it over the line, it would be just a catalyst. This is kind of a weird reaction though. The predominant reaction, it is mostly acting as a catalyst. So if you did that above the line, you're good. It is not a reversible reaction, which is why I have a really nice big arrow there. Not reversible at all. We have solid carbon in there now. And the question is, can we touch it? Not right now. Tomorrow I'm going to take the best one of them all and I am going to neutralize it because there is a lot of acid still on it. A lot. So I will neutralize it and then we will put gloves on, and if you want to touch it you may. It's just solid carbon. And water. Does it look watery in there? Yeah, that's where all the steam was evaporating out. So we said that we could increase the rate of a reaction by stirring. Most of the time that is absolutely true. And I could have increased the rate of the reaction here. However, it would not have been as awesome as it is, and it wouldn't have grown as much because the reaction, if I stir, I would have made more of the bubbles pop out sooner before the carbon had formed. The carbon needs to form, and then the bubbles push the carbon out because the gas pushes it out. So that's why we got it as big as we did. If I had continued stirring, I would have gotten the bubbles, that water steam out before it was able to fully make the carbon, which would not be good. So that's why I did not stir as much as we would have thought if I wanted the reaction to go faster. We do know that it's an exothermic reaction, so my delta H value is negative. And that's why we're not touching it right now, because I don't want any of you getting burnt. We smell stuff. You probably smelled it when you came in today. It's gross, right? It smells like a perm or something. Yep, that's sulfur. That's the icky sulfury stuff. Those are the byproducts. It's like when you have your gas tank. Normally combustion yields just carbon dioxide and water. And in an ideal world, that's all you would get. Then we'd be clean burning of the fuel. It would be awesome. However, we have a lot of byproducts, and that's what we get here, and that's why we get the smell that we get here. We're forming some of that sulfur dioxide, the sulfur trioxide. We're forming not only the water, but also carbon dioxide, potentially some carbon monoxide as well, which is why it's in the fume hood. It's good and safe for us in there. But all of those byproducts are what makes it smell icky, and those byproducts are what make gasoline engines bad for the environment.